Hello everyone, today we are going to derive E equals mc squared. Let's begin. So first of all, E equals mc squared, it's a pretty famous equation. It just says that the energy of some system is the mass of the system times the squared value of the speed of light. That's just it, and let's derive it. So first of all, we have to define some concepts. So you have to define what force position is. Now we know from relativity that we have a dimension of time and we have a dimension of space, right? And we can have things called world lines in this space-time, and we can have tangent vectors along the world line. The world line is parameterized by lambda, and then our tangent vectors is dr over d lambda, which we can relabel as x with a chevron on top of it. So there is a rule in relativity, which we could derive in principle by using the Minkowski metric and some other things. But there's a rule that the dot product of tangent vectors along some path in space-time equals the speed of light squared. Or in other words, x vector dotted with itself equals the speed of light squared. Now this is where the idea that things or all things in space-time travel at the speed of light comes from. Because the dot product of any tangent vector in space-time with itself is the speed of light squared, so the square root of that is just the speed of light. So this is why you see some people saying that we all travel at the speed of light, but this of course is more. It isn't really correct to say that we travel at the speed of light in space-time, because remember that this x vector does not represent velocity of a particle, nor even velocity through space-time. It just represents the rate of change of some. Well, it just represents the tangent vectors along some path. It doesn't actually correspond to the normal, usual velocity that we know. So that's where the idea comes from, but it's really just more of a pop sci relic, if you ask me. But that's the gist of it. The dot product of some space-time tangent vector is going to be c squared. Okay? Now we define momentum, or the force momentum, sorry. The force momentum is defined as mass times the rate of change of the force position vector, x vector, parameterized by proper time. We can choose a different parameter, but usually we work with the parameter of proper time, given some, inertial frame of reference. So a quick thing to note here is that for momentum, this p vector, again, it isn't the momentum of a particle. It's something else. It's analogous to the normal momentum, but it isn't the same thing. The force momentum, if we can recall from relativity, has components of E over c, then p1, p2, p3, given some basis ei. Now these bottom three components, these correspond to the actual momentum of the particle. However, the first time entry corresponds to the energy of the particle divided by the speed of light. So now let's actually evaluate what the dot product of the force momentum vector with itself is. That's just going to be m times this m times this. Oh, also, I should have mentioned it should be dx over dt. That equals the speed of light squared. That's my bad. It should be dx over dt, not just x dot with itself. It should be dx over dt. So essentially, x, right? X is just x are the tangent vectors along some path, and then dx over d tau would be the rate of change of those tangent vectors along the proper time coordinate direction. Anyways, let me think about this for a second. Yeah. Okay, so anywho, again, so it should be the dot product of x vector over d tau with itself. It's not x dot x equals c squared. I meant to write this over here. Dx over d tau dot with dx over d tau. So here we have m squared times dx over d tau dot with dx over d tau. So that's just m squared. This is going to be c squared with our rule over here. So this is going to be m squared times c squared. Now recall that p is this over here, this p vector. So essentially we have the dot product of p in itself. Yeah, so if this is the p vector, then the dot product of p with itself is going to be e over c p1, p2, p3 times e over c p1, p2, p3 times the Minkowski metric. Or in other words, it's going to be equal to p nu p, or I'm trying to think of how to write this. Yeah, p nu p mu, and then the Minkowski metric mu, essentially. Or in other words, the dot product of the forward momentum with itself is going to be p naught minus pi minus p1 minus p2 minus p3. All right. Now recall that we just said that the dot product of the forward momentum with itself is going to be m squared times c squared, right? So this over here is going to be equal to m squared times c squared. Now I want to make our notation a bit more compact. Recall that the bottom three indices correspond to the usual momentum, right? So we can just define this term to make it be a bit more compact. You can define this term as being, let's call it p squared, or yes, let's call it p squared. To be a bit more exact, let's define p as being p1 plus p2 plus p3, or wait, there's some problems with saying that, right? Okay, sorry. I mean, let's define p squared. Yeah, it'd be more wise to call it p squared. Let's define p squared as being p1 plus p2 plus p3. And that would mean that this term, over here is just p naught minus p squared. And of course, remember that p naught is e over c. So this is just e squared over c squared minus p squared. And that is, of course, going to be the dot product of the forward momentum with itself, right? Now recall that the dot product of the forward momentum with itself is going to be m squared c squared. So this is also going to be m squared c squared. So now we have like e squared over c squared minus p squared equals m squared c squared. We can multiply both sides by c squared to get e squared minus p squared c squared equals m squared c to the fourth. Then we have e squared equals p squared c squared plus m squared c to the fourth. And we can look at the case where p equals 0, or the center of mass frame. Well, sorry, not center of mass frame. We're not doing scattering here. But we can look at this specific case where p equals 0. Then we get e squared equals m squared c to the fourth. Take the square root of both sides, you get e equals mc squared. And just for kicks, we could use natural units where c equals 1, like I believe light meter per second or something, some natural unit. And we'd get e equals m, which is mostly used in QFT books. But yeah, and that's how we derive e equals mc squared. Now, of course, this actually applies only for the case where the momentum is 0, which is which a lot of people don't know about. So this is only a special case scenario. And that's how you derive e equals mc squared. Bye.